I don't have.
Yeah. At least we don't have lab every week. That's every other week.
Isn't in here.
Okay, well, let's go ahead and get started. So homework is going to be due tomorrow, right?
Yes.
It's tricky homework, isn't it? Yeah, Newton's second law stuff usually is fairly challenging. And so if you're struggling with it, believe me, you're not alone. So what I'd like to do is do some examples. In particular, I think going down slopes will be a big part that we haven't covered yet. So that's what we're going to do. So start out with, there's several problems like rolling down, like a car rolling down a hill with acceleration, that type of thing, that are on the homework that we would like to be able to do. And so I'm going to do a general block going down a slope problem, and then you should be able to apply what we do here to those types of problems anytime you have something going down a slope. All right, so the general type of problem, just so we're all on the same page, it's often called the inclined plane problem. And the idea is that you have some sort of slope, so or ramp or something like that, hill, to represent like a triangle. And the angle of the hill or the slope with respect to horizontal we'll call a general angle theta to start out with. I know we don't like symbols, but you can plug in any angle you want later on. You don't have to mess around with this, a specific thing. And the idea is that you have a block, some sort of mass that's going down this hill. And we want to figure out we want to kind of understand this problem. Once we understand the problem mathematically, you can figure out all sorts of things about it, whatever you want to find out. In particular, maybe, let's see, find acceleration. So let's start out with the simplest example where this is a frictionless plane. So maybe you can think of this as ice going down ice or something like that. So frictionless plane to start out with. All right. So when you have a situation like this, I'm going to go ahead and draw a free body diagram, but in this particular case, I'm going to leave it. I'm going to draw forces actually on the block on this picture, not this isolated, just so we can see some stuff first. What are the forces on here?
The weight force going straight down.
Yeah, the weight force would go straight down towards the ground or center of the earth, so that's the gravity force.
The block pushing back out.
And which way does that go?
Perpendicular to the surface.
Yeah, perpendicular to the surface.
Exactly. Normal forces are always perpendicular to the surface. So we have a normal force like this. Any other forces?
Gravity or
That's it, actually, if it's frictionless. If I had friction, I'd have another force. So the key thing here, and by the way, these forces aren't drawn to scale very well. The key thing here is for these problems, and this is key, is to use a slightly different coordinate system than normal. We're going to use a tilted coordinate system and have x direction being down the plane and y direction being perpendicular to the plane. Then the normal force is in the y direction, exactly. Even when I start to have friction forces, it would be exactly in the negative x direction, something like that. And this makes this turns out to make things a lot easier. The acceleration is purely going to be in which direction?
The X direction.
Yes, and that's why this is such a convenient thing to do, is we only have acceleration, the X direction. The acceleration in the Y direction perpendicular to this plane is going to be 0. All right, so probably the key thing is to split up the vectors in components along each of the coordinate axes. So normal force already points all in the Y direction, right? We want to be able to figure out what part of the weight points in the Y direction and what part points along the X direction. So if I draw a little triangle here, like this, where this side's along the Y direction, and this side is along the X direction, or parallel to that plane, this would be the the Y component of X, Y hat, and then this would be the X component of the weight, X hat, Y component of the weight.
Where's what, 90 degrees? Is
And
that,
then this is a 90-degree angle right here. If only we knew what this angle was, we would be all good.
It's the same angle as.
Well, that's, yeah, it turned, you can sort of
Ends up
see, you
being
can sort of guess. Now we'll do this, we'll do a proof of this. But you can sort of guess that as I move this angle down, this angle would also move down. Maybe you can see that if this angle were 0, this would be 0. If this angle were 90 degrees, this would be 90 degrees. So maybe you can sort of see that this angle is going to be related to that angle. But let's prove that actually this is exactly the same angle. I'll write this just, and then we'll prove it. So, maybe if I draw the weight vector coming straight down here, it might be a little easier to see. So I just moved the vector down to the edge of the block here. So this is a 90-degree angle here, right? So I'm going to get rid of that W so it doesn't get in the way. So this angle here is 90 degrees minus theta. So that theta plus this angle plus this 90-degree angle is going to be 180 degrees. Okay? This angle here, this line coming straight down, that's perpendicular to this plane. So this is a 90-degree angle here. So if this 90-degree minus theta's this angle, and this whole thing's 90 degrees, that means this is going to be theta. Okay, so that's the formal proof of that. And so let's go ahead and we automatically know what the magnitude of this weight is m times v, right? And so how much of that points in the x direction? If this is the angle theta, what's this side of this triangle? This length here is mg.
opposite
So
over,
this is opposite
so
that
the
angle.
opposite over and
Sine.
sine.
Sine of theta
Mhm.
would be x, the weight in the x direction,
Over
mg.
Mhm.
So that means weight in the x direction is going to be mg sine of theta. All right. So, if I'm summing up forces in the x direction, setting that equal to mass times the acceleration in the x direction, what forces are in the x direction on this block?
Just
That.
that.
Just to
This
that.
is part of gravity. It's the only force in the x direction in this case.
Mhm.
So I would have m v sine theta is m times the acceleration in the x direction. If I wanted to get the acceleration in the x direction, what should I do?
Oh, divide by the mass.
Cancel, and I get that G sine theta is acceleration in the x direction.
Mhm.
All right, this is good for a frictionless plane. Where there's
But-
no friction.
So do we have to do the y too? Does it accelerate during?
Well,
And
so
then
what's
we'll
the
also-
acceleration in the y direction as we have it? Does it go through here?
Oh, 0.
Yeah, that's the beauty of this tilted coordinate system, is the acceleration in the y direction is going to be 0.
Okay.
That makes sense?
Yeah.
You want to do a slightly more tricky one?
Sure.
All right. I think there's a homework problem
Yeah.
where you have a car going down a hill. What's the
Yeah.
angle of that hill?
15.
All right. So you have a car going down a hill at a 15, and this is 15 degrees, okay? Now, let's do the first part of this problem. The first part was, what's the acceleration, right?
Yeah.
I mean, you guys already know that, right? What's it gonna be?
It'll be
9.8 sine.
yeah,
15.
sine of 15 degrees.
Yeah, it'd be 9.8 meters per second squared, sine 15 degrees. And that one's pretty straightforward. You can just evaluate it at
2.54.
Uh-huh.
2.54.
Yeah.
All right, now the last part of that problem has something else. It says,
That's friction.
now suppose that you have friction,
Mhm.
and that the friction force exerts 5,000 newtons.
5,000. Uh-huh.
5,000 newtons this way. By the way, what was the mass of the car?
It was 2,200 kilograms.
2,200 kilograms. All right, what I'd like you guys to do is, if you can you take about 5 minutes, draw a free body diagram for this block, but this time there's friction. Sum up the forces in the x direction and set the result equal to MA. And see if you can get A. So it's exactly that same problem, but now you just have one more force in the x direction. But any guess? And you know what that force is.
So I didn't like use the threshold. So I just plugged in. And G times sine of theta is equal to n AX. And so I have I got the newtons in the first.
I did that too. It worked too.
And so is that what? So then I just took the 9 meters minus the 5,000 and then I calculated
Yeah.
back.
That looks
Yeah, you can do it that way too.
So draw a free body diagram and show it. And help someone. Next.
Dr. Green.
forgot that, yeah.
Yeah, I forgot something.